will talk more about the last lecture. Well, this is about some things that we were working in Bariloche, in the group of Bariloche the last years. The people involved in this is all here, so it's Javier Magán, Marina Huerta, and Valentin Benedetti, and well, there is another student, Diego Pontello, that is already left physics. So, well, this is about, we started working on entropies in quantum field theory, and entropies are naturally some quantities that are attached to algebras in the quantum theory. So you have a state, and you have a reduced state to some algebra. In more precise terms, people say reduced to some region, but it's in fact reduced to some algebra. And then immediately this makes contact with a version of quantum field theory where you are interested in algebras rather than specific operators. And this version is very old. This Hag-Kastler version of quantum field theory. And so we started studying this subject, let's say. And then we were interested in symmetries. Of course, you always are interested in symmetries in physics and how the symmetries are related to entropies. And there were at the time several problems or features that, for example, some coefficients in the logarithmic term, the Maxwell field, that do not match the anomaly. We wanted to understand that. And we also wanted to understand, people was discussing how to define entanglement entropy in a gauge theory, how you cut in the lattice. We made some papers on that. We made some papers studying different choices of algebras. Perhaps some people in the audience know these works of electric center choice, etc. And we concluded that there was no difference regarding to the continuum limit for a gauge theory and, let's say, another theory like a scalar field. But this pertains mainly to the continuum limit. So the ultraviolet problems that you find, the ambiguities in the entropy are the same. There is nothing special about gauge field or non-gauge field. In fact, you have some theories that you can specify a gauge field or dually without a gauge field. So there is no problem with that. But in the process of studying this, we discovered that there were some features that are now macroscopical and are related to the textures of the algebras in a quantum field theory, but these are not ultraviolet problems. These are really physical stuff. And when you do that, you realize we were studying this, and we realized, oh, these things are the same as people recently have studied, and they call it generalized symmetries. So I will talk about a version of generalized symmetries from an algebraic point of view. I warn you that this is a very Bariloche Center view of this subject, and some people maybe do not agree with all we say, and we don't agree with some things they say. So I will try to connect these things. What else? Well, please ask questions. All what I will say is very simple, extremely simple, embarrassingly simple, they say. So please ask questions, and perhaps all the members of the group can answer this question. So where will I start? So one important thing is that I will talk about algebras and algebraic description, etc. And I want to convey the message that you don't need to be a mathematician, because this subject was studied for a long time by mathematicians especially, or mathematical physicists. And because it requires some some tools like von Neumann algebra, some type of special von Neumann algebra, etc., that are very kind of mathematical things. But even if you study quantum field theory with fields, you don't really have in mind that these are distributions or operator value distributions or all the Wyman actions, all that. I think you can think of the algebras in the same heuristic way, and you can learn things with this different point of view. So it's important to emphasize that. So all what I will say, most of it is without any technical details, or very few technical details. So my first thing is quantum field theory. So quantum field theory is a quantum theory, ordinary quantum theory, but it has a special feature that it has a space, right? It has a space, and the space is immersed in the quantum theory as what? As what is a space? Is a set of regions where you have operators inside, so it's a set of algebras, in fact. So a quantum field theory is a quantum theory with some preferred set of algebras for regions. Let me call R of A. This is an algebra of operators, and this is the region, right? So what is an algebra? An algebra is a set of operators in Hilbert space that is closed under multiplication, linear combination, adjoints, and we also take the identity as belonging to the algebra. One technical detail is the only technical detail I will talk about is that in order to be an algebra, operators have to be multiplied and are still operators, and for that you need bounded operators. Bounded operators are operators that have bounded, let's say, a spectrum. So they have a full domain in the Hilbert space. They can multiply any time, any number of times. And, and usually, if you start with a quantum field theory described by fields, phi x, this is it's not a bounded operator, but it's not also an operator. If you multiply phi x to the vacuum, for example, this would be a state, but this state has infinite norm. Phi x is infinity. So it is not an operator, so you have to smear it. So you define some phi alpha, some integral of some function, phi x. If this function is of bounded support and is smooth enough, then this is an operator, but it doesn't guarantee that this thing is bounded. In general, to make it bounded, one exponentiates it, for example, and this is a unitary, and then it has eigenvalues that are norm 1. So, or you can also decompose this in projectors, and projectors are also bounded operators. So this is the technical stuff. It means that you are making these algebras out of these things instead of the field, but you can, in general, do this. So this is the first thing. So this description of a quantum field theory in terms of the algebras instead of operators is Haag-Kastler description. And the important thing is the information of the theory in this case is in what is called the net of algebras. That means what are the subalgebras that we are interested in and how they relate to each other. For example, this is a smaller one, etc. This is the information is there. So this is a kind of coordinate-free description. Coordinate-free description means that, for example, if you have a field, for example, a free field, phi x, and phi x cubed they both give place to the same algebra. They are describing the same theory. So you can choose this one or this one. It will give you the same thing. So here you have a coordinate-free description because, as mathematicians always do, they put all possibilities there. So you have all the possible operators inside, right? So in this sense, it's very similar to the bootstrap approach, where people describe the theory with all operators, all descendant operators, all the primaries, right? It's somehow similar in spirit. You have the full algebra of operators to describe the theory. So, well, the second point is von Neumann algebras. Suppose you have a set of operators, let's call it C, some O1, On. It can be infinite. And then you take the commutant, C prime is all the operators such that all commute with OGI is equal to 0 for all I. So this is the commutant. This is a set of operators in Hilbert space, bounded operators, that commute with all this. So this is always an algebra. This C prime is an algebra. And a von Neumann algebra is some A such that A is equal to A double commutant. Is equal to its double commutant. So in infinite dimensions, what is this? This is kind of strange. Well, in finite dimensions, all algebras are von Neumann algebras. All algebras are described by this equation. In infinite dimensions, there are the subtlety of when you have an algebra, you have to say what is the topology under which it is closed. And this can vary. So von Neumann algebras are closed under some specific topology that is called weak topology that is very physical. So closed means that if you have a set of operators, a series of operators, this converges to some operator and is also belonging to the algebra under some topology. Here the topology is very physical because it tells you that this limit operator cannot be distinguished from the tail of this series by any physical measurement or a finite number of measurements with a finite precision. Yes?
Sorry, let's go ahead and push a bit. So why, for the finite dimensional case, why can't C prime have things that commute with everything in it that would then be in this double commutant?
Sorry, what did you say? Say again.
So that the C prime is the set of things that commute with everybody in C.
Right.
And so it's clear that if you take the double commutant, C is going to be contained in that. But I guess it's not obvious to me why it's equal. Like, why can't C?
No. In general, it's not equal. In general, it's not equal. If you, for example, somebody give you two matrices in some space, and you want to find the smallest algebra that contains the two. Then you start multiplying, you start taking linear products, linear combinations. This is a mess, and you will get products, etc. And this is a cumbersome thing to produce. No? But if you, instead of doing that, you take the double commutant, it's very simple, because you have to do a linear problem. You have to do first the commutant, and commutations with your two matrices is just a linear problem, and then the double commutant. And then this is the smallest algebra, so it's very practical. So this von Neumann theorem is very practical from the practical point of view to see what is the algebra that is the smallest one that contains some set of operators, right?
Okay, so sorry, because I had said that, for finite dimensional things,
Right.
everything is a non-linear?
No, every algebra, closed algebra. No, every set of operators, but every closed set of operators, closed algebra, right? Yeah? So it's another, it's something very nice, this von Neumann theorem, also because it allows you to talk about algebra without caring about much of topology, that for physicists, the topology is something weird. So it's purely algebraic notion here, right? So the third question would be, if all regions, have different algebras. Well, and this is the answer is in general no, because, for example, you have, we are in a relativistic theory here. You have this region that is like, this is time. So this is a double cone, people call it, or diamond. These are light directions. And then if you have an operator here, in general, you can write it down there with some other operator here using the equation of motion. So this region and this diamond will have the same algebraic content, are the same thing, right? Also, if you have a stress tensor, for example, you can smear the stress tensor here to take an operator here and move it up using like time translation, but time translation reduced to some inside the diamond here. So it's I'm making a Hamiltonian that only works in this region, right? So if you have a stress tensor, this is always the case. So these algebras are the same. So in general, the algebras will be attached. So there are counterexamples, but they are quite pathological, these generalized fields. So we will assume this, and then any algebra is attached to a diamond like this. So it's a causally complete region. And then with this idea, we are going to describe the algebras. I'm taking t equal to 0, a slice, and any algebra here, or this other one, that has a diamond attached, I will forget about the diamond. I will talk about only on the intersection of this thing. So this is, so with the t equals 0 plane. So for me, the algebras will be attached from now on. I will be attached just to a spatial plane. So when I draw this, I will mean that this is this part of a diamond, right? Yeah, it is. So what this means is that I'm not in this talk interested in relativistic things. I'm interested in only the spatial features of these algebras in some plane. So, and this will make much more contact with lattice theories, for example. You can use all these things only for a lattice. It's the same thing. The next point is quantum field theory is local. What does it mean? First of all, we have to understand what it means that this algebra is attached to a region. What this means, what exactly this means. And in general, this word local has two different meanings. The first one is additivity. Additivity means that the algebras are generated by smaller algebras, by smaller things, for example, field operators in arbitrarily small regions, or in a lattice, something on each side of the lattice, for example. So additivity means, in more precise terms, that you have some region here divided by 2, and the algebra of R is equal to the algebra of R1, union the algebra of R2, but the union doesn't make an algebra, so we have to close it with the double commutant, and this operation is called, is written like this, with this symbol. So this is just the name of the algebra that is the smallest one that contains the 2. So this is additivity. If you were to produce it with local degrees of freedom, you will have immediately additivity. And the second meaning of locality is also called causality. And what does it mean? It means that if you have two regions, the algebra of R1 is included in the commutant of the algebra R2. So all operators localized here are commuting with this one. This in relativity is just it's a causal propagation of signals, let's say. But in the lattice, it's just what people do, right? At t equals 0, things commute. So these are the two meanings. Let me say this property, I will call it R8, R1, is included, in fact, not in R2 prime only, but in the whole thing outside prime. So I will call it R1 prime, if I have this R, I will call R prime to the complementary region, to the outside part. So it means that the algebra in this region will commute with the algebra outside. So, and then we have this simple property, and one can ask whether this is saturated. Because you start thinking about algebras, so you have a new question here, whether these two things can be equal. So this gives me the next point, this completeness. Equal to Haack duality. Now I'm going to so if you have that the algebra of R is less than the algebra of the complement prime, it means that there are some operators that could be put in the algebra of R that are not there. So it's not as full as you can take this algebra. And this, we call this is non-complete. While the case that the algebra of R is equal to the algebra of R prime, this is called in the literature Haack duality. That here is what I'm calling a completeness. We will see later that this idea of completeness is the same idea that people have thought about. The complete theory, people talk about this when you have a lattice, a full lattice of electric and magnetic charges, all that kind of thing. Well, this is exactly the algebraic version of this. It's called Haack duality. In general, the people in the algebraic community talk about Haack duality only for balls, for region with simple topologies, but in general, one can discuss also Hug duality for regions with different topologies. And then completeness would be to say, in this sense, that the algebra generated by the local degrees of freedom is the maximal one compatible with causality. So it's the maximal one that commutes with the outside part, right? Another thing is that this idea of completeness, so it's the usual idea of completeness that people have in mind, but it's more precise version, and it's equal to modular invariance for CFTs in D equal 2. So this, I will not talk about this, but Valentin Benedetti will talk about this next week. So the next point is Hug duality violations. Hug duality violations, that is the main subject of my talk, right? I'm not interested in the case of complete theory. For example, a free scalar will be complete theory. But in the case when there are Hug duality violations. And I will try to make the idea that this is equivalent to generalized symmetries, so a description of generalized symmetries. So what happens in this case? In this case, we have that the algebra of R is included and not equal to the algebra of the complement prime, to the commutant of the algebra of the complement. So this algebra will contain this one, but will have more operators. And I will call this, with this letter, with a hat here, and I will call it the maximal algebra. The maximal algebra that you can attach to the region R without violating causality, without non-commuting with the local operators, the field operators outside. So if you want to ask questions, ask loud, because I don't, I'm too attached to the thing to see. The operators that are in the boundary. Right, it's an important question. There are no operators on the boundary in a continuum theory. So this is something that somehow simplifies and also complicates the case of continuum theory. In a continuum theory, you don't have operators in the boundary. If you smear a field operator on the boundary alone, is D minus two-dimensional object, is not enough to make it a field operator. It's still a distribution thing. So there are no operators on the boundary, and this means that all these algebras for any quantum field theory, in any dimension, in any region, are factors. It means that they don't have operators that commute with all other operators of the algebra. For example, sorry? Well, then you are destroying my space, right? But you can impose boundary conditions, right? No problem. But this will be a boundary in the space, right? Yeah, but then there are still I think there are no operators. Well, you can put there another theory living in a lower dimension. Yeah, you can do that. Yeah. But for the continuum theory, there is nothing in the boundary. So this makes a factor, and also I haven't said, but it is supposed that all these algebras for any region are the same object, the same mathematical object, these type 3 algebras that are unique type 3 1 algebras that are unique. And so it's like a Hilbert space. All the Hilbert spaces are equal. It doesn't tell you anything. So you don't get any information from the algebra itself. You get information from the relation between the different algebras. This is the idea, right? So this is the maximal algebra. And then, as it contains AR, it must be that this maximal algebra is equal to the algebra of R plus some other operators. Some other operators, I will call these operators non-local operators. Non-local operators because they commute with the operators outside, but they cannot be formed, they cannot be generated by field operators in the region R. When you have this structure, it's interesting that you get a bonus directly that the same thing will happen, that the maximal algebra is not equal to the algebra itself, but has more operators for the complementary region. So you can draw this complementarity diagram. You take the algebra of R. This is included in the maximal algebra. That is equal to AR plus some other non-local operators. And then if you take commutants, the maximal algebra, the commutant of the maximal algebra is the additive algebra of the complementary region. We define it like this. So this is the algebra of AR that will be included in the commutant of the algebra of R is the maximal algebra of the complementary region. Prime, sorry, this is a prime. And this will be equal to the additive algebra of R prime plus some other, let's call it B, some other non-local operators B. And you could say, well, why is this always different? Well, if you started with these are two different algebras, and you take the commutants, they cannot be equal. Because otherwise, taking the commutant again, and using the fact that the double commutant gives you again the same algebra, it will imply that these two are equal. So if these are different, these are different. So if you have non-local operator for a region, you have dual non-local operator for the complementary region. And this cannot be avoided. Another thing is that when you have this situation, these A's and B's cannot commute to each other. The A's, the non-local operators for complementary regions, cannot, all of them, commute. If they were to commute, suppose they were to commute, it means that A maximal of R commutes, is included in A maximal of R prime, the commutant of this, because they commute. I am assuming that. But this thing is just, by definition, this thing is the additive algebra of R. So it means that these two are equal, and so you don't have any non-local operator at all. So it must be the case that these A's and B's are not commuting to each other, at least not all of them. Another point is that in general we have an infinitely many set of operators that are non-local in a region. But But you have, if A is non-local, then the sum of O lambda, A, O lambda prime, with O lambda prime belong to the additive algebra. So this is also a non-local operator. Will not commute with operators in the complement with non-local operators in the complementary region. So it means that you will mainly be interested not in each non-local operator, but in the classes of non-local operator that are moved among themselves by the local ones, by the additive ones. So this is the important objects that you want to consider. So it could be the case that in many cases these classes are kind of finite number of classes. So it's not, could be infinite also, but even if non-local operators are infinitely many always. So let me give some examples. I will start with an example that is a little bit peculiar, but it's an example where the region where you have non-local operators is trivial topology. So the topology of a ball. So we will have a ball with non-local operators. So this is the case, for example, of the free Maxwell field. In d equal to 3. Not d equal to 4, but d equal to 3. In this case, if mu nu is equal to where this is a derivative of a free scalar field. So we have this identity of the gauge invariant operators here and the derivative of the scalar field, and people, if you describe it with Lagrangian, we will say, well, these are dual, these theories are dual to each other, but here, from the algebraic point of view, they are exactly the same object. There is now no difference at all between these two theories, but it's important that it's not that the Maxwell field is dual to the scalar field, it's dual to the derivatives of the scalar field. So it's as well, but here is no difference at all. No, they are not doing it. They are the same. They are the same. No, but you are talking about things that are not physical, like the gauge field itself, a mu. But I'm talking about gauge invariant things, and then they are exactly the same things. There are no difference at all. You can say, well, they are dual because I describe it with different Lagrangians, let's say. But physically, if you want to differentiate between the two with some measurement, you are not going to. So here are free. No, are the same. Are exactly the same.
Properly defined, they are the same. They act on different states.
So maybe just concretely, the shift symmetry of phi is related to the conservation of flux?
Yeah. I will go to that, right.
I mean, I would normally say that the phi field there is quotation marks is a constant field.
Yeah, exactly. This is the case.
And one is essentially a gauge field.
Yeah, but it's a Goldstone field. It's exactly the same thing. It's exactly.
It's true that 2 plus 1 dimensions, the gauge theory, is only one photon, and that sense is identical to the particle quantum of the theory.
No, it's not only the particle content. All the operators in the local region are exactly the same. You cannot differentiate between them at all. There's no difference. So, no, I put it in this example exactly because of different perspectives that can give you looking at algebraically. So, we have made a paper with Marina, and it's exactly the same also in the lattice. You can do it in the lattice with a description of for the free electromagnetic field that is exactly the same as scalar. It's the same thing. You have the operators, the electric and magnetic operators. In the links, they leave the electric operator. In the plaquettes, they leave the magnetic operator. And then in the plaquette, you have the momentum operator for the field, and here it leaves the derivative of the scalar, right? So they're the same. So, well, in this case, what happens? What happens is that you can build up some, of course, the trivial thing that you can put here that commutes with, here I have the, let me put the version of the scalar. I have the derivative of the scalar, and here I can put the scalar itself, right? So immediately it commutes with everything outside, right? It's trivial. And instead of that, I can build up these operators that are exponentials. With the integral of alpha x equal to some q, some charge. And then I can put here my phi q, and this is a non-local operator. And what is the dual non-local operator? The dual non-local operator is the twist here, some operator here. So so this theory has a conserved current equal to 0. So it means that J mu equal to d mu phi. This is a conserved current. And then you can construct the charge. That's the integral of some beta x J0. And I'm taking this beta as equal to 1 here, and 0 outside, and here I have some smithing function. Then, if you exponentiate this charge, you will get that, let us call it tau. Tau is a twist. A twist is an operator that implements a symmetry inside some region, but that do nothing outside, right? So this twist is exponential of this charge. This charge is localized in some region B. And then you have just displaces the scalar, so it means that it will do nothing. It will do nothing to the derivatives of the scalar, and then you have also this tau g commutation relation with this. So we have this operator now that commutes with local operators. Local operators here are the derivatives of the scalar. It doesn't commute with the charge operator, with the exponential of the field itself, with the other non-local operator. So this is a non-local operator in the outside part, because it commutes with the additive algebra that is just the derivative of the scalar. So you have this maximal algebra of the region R is equal to the additive algebra plus these phi q's, where q belongs to the reals, and the maximal algebra of the region R prime is equal to the additive algebra of R prime union these tau g's with g belonging to the reals. So you have non-local operators that are labeled by a real number. So in this case, you have a kind of group of non-local operators that is the reals, and the group of non-local operators of this one is also the reals. These are dual non-local operators and have these commutation relations.
So can your field phi wind around this region? The mean trivial winding number?
So this is here. No. Winding number?
An operator that's actually, maybe, I'm going to put my condensed matter hat now.
Right.
I'm going to call phi the phase of a superfluid. And I think,
It's non-compact, yes.
oh, it's non-compact.
Yeah, it's a free field, yeah.
No, it can be free field and be compact. Has to be periodic.
Yeah, well, that would mean that I'm, well, for me, a free field compact in the sense you say, is to take here the phi q's, some specific ones that form a group of integers, right? So that would be the compact case. So, and then the non-commuting ones will be some U1, and you have that. But these are all intermediate subalgebras from the additive algebra here and the additive algebra outside, and the maximals. So you can take intermediate algebras, but they are not going to be additive in this sense. So you can take, well, these are exponentials, so I take it as bounded operators. Phi is not a bounded operator. With respect to alpha, yeah. So, yes. But this is a generator, right? The generator is not bounded. It's a generator of a group, and it's not bounded. So, for example, time translations are unitaries, are bounded, energy is not bounded, right? So, you can see here that these non-local operators have fusion rules. The multiplies these two is just additive, and here the same. So they have all these kind of fusion rules and commutation relation between non-local operators that is general. So one can think this example can be generalized to any group, any symmetry group, but the problem is that in general, if I have, for example, some theory that let me call F, people usually call the field F, and then this theory have some global symmetry group, as this one here, right? So if I take the neutral part, so I quotient by the global symmetry group, I take the neutral part of the algebra. This is another theory, let me call O. And so here is something like this, right? You have the field, the scalar field. If you take the neutral part and then the translation, you get only the derivatives, right? It's something like that. It's very similar to this. But if the symmetry is unbroken, what happens is that if you start with this, you will go to a Hilbert space that is neutral, and you will never have in the Hilbert space these operators that are charged. So this special case where you have Haack duality violations for a ball is only happening when there is a spontaneous symmetry breaking. As Eduardo was saying, this is exactly the case of this scalar field because it's kind of a Goldstone boson. So in fact, for example, this operator, phi, these phi alphas that are charged operators, the expectation values are different from zero, right? Are not zero. So this is why the symmetry is broken. the symmetry is broken. So in general, when we have this structure, we cannot have Hug duality evaluations for a ball. This is very general. In general, you don't expect Hug duality violations for a ball. In particular, for example, for conformal field theories, you don't have Hug duality violations for a ball. Well, somehow this, if you act with this operator to the vacuum, you will generate the field itself, the field phi. In the focus space will appear this, because the vacuum does not respect the symmetry. That's the thing. So this is why you will have this operator available in your Hilbert space, right? While if your vacuum respects the symmetry, acting with neutral operators, you will get only the neutral Hilbert space and not the charged ones. But it's something that I will not detain myself much here. This operator is charged, it's not invariant, right? And this is why, if it were not spontaneous symmetry breaking, you will expect this equal to 0, because it's charged, right? Right? So, but in this situation, when there is no spontaneous symmetry breaking, still you have Hug duality violations, but for regions that are with topologies of more than 1 balls. Just 2 balls or more. So this is a case where you have Hug duality violations for regions with non-trivial pi 0, so disconnected regions, or complementarily with non-trivial pi d minus 2, regions we have non-contractible surface of that dimension. For example, in 2 balls, for the case of 2 balls, you have this, for example, for a symmetry, any symmetry. Okay. Okay. The black one, right? Yes, this is good. For example, if I have some charge operators, some representations, and then I sum over this, let's say, the zeta projection or whatever, and this will be neutral operator. This will be a neutral operator on the symmetry, and the global symmetry, but cannot be produced locally by additive operators, or neutral operators here and neutral operators here. It's something non-local for these 2 balls, and in fact, it's immediate that it commutes with every neutral operator outside, so it's a non-local operator for the 2 balls, and we have dually some twist operator that acts as the group element only on one of the 2 charges, right? As the symmetry is unbroken, this twist is equivalent to a twist going to the other direction and acting on this. So there's no difference because the global symmetry group is the identity here. So if I take the twist here and the twist outside, I multiply is the identity. So these are the 2 non-local operators, and this tau c is in fact the sum over the elements of the group in a class, in a conjugacy class of the group of the tau of the group elements. This has to be taken as a class, because it has to be a neutral operator of the full theory. I'm taking only the neutral theory here. So in this case, you have non-local operators for the case of topologies with 2 balls or the complementary region that is a shell. And these are labeled by conjugacy classes and by the elements by the representation of the theory. And you can see, for example, for a finite group that the conjugacy classes and the element and the representations are the same number of elements. And in general, there is an abstract notion of the size of these Hug duality valorations that coincides for the 2 complementary regions. So one has some commentaries here, 2 commentaries. One is about topology. We see that if you have, for example, this twist, it can be deformed. By, for example, adding a little piece here. If you have, for example, this twist is an integral of a current, then it can be deformed just by adding something that is produced entirely by local operators. So in the same class will be other operators that are deformed. It has the same topology, but they are deformed by the additive algebra. And this is in general, one can also use, for example, the stress tensor to deform. You have the charge, for example, anti-charge, this charge-anti-charge operator, and you can take, for example, some smoothing of the stress tensor to displace this charge and to move it, for example, to another position or to deform it. So it means that the Hug duality violations are a property of the topology of the regions. And this is called transportability. And it matches very much with the idea that what you are looking for is something that can be used to classify theories, because it's a property of the net. It's something that it's a topological property of the net of algebras. It's something on the structure of the algebras and regions, right? And it can also be used as an order parameter. I will talk more about this in the next lectures. Because of that, because it's some property of the net of algebras that somehow determines some kind of some feature of the net of algebra or the theory. So this is an important property. And another commentary is that the idea of non-local operator. So this, let me say, that this is what people call a topological operator, right? These non-local operators are topological in that sense. Can be deformed to other topological operators. And the other idea is that this non-local operator is a relative notion. Relative to what? Relative notion to the region. To the region R. For example, in this example, if you have a ball with 2 charges, plus and minus, this plus and minus will be non-local operator for this two-ball region, but will be a local operator inside a bigger ball. This theory has Haack duality for balls, so there is no non-local operators for two balls, for a single ball. It's a non-local operator for two balls, but it's a local one or additive one for one ball. So this idea is that, for example, in general, when we have Haack duality for balls, it means that any topology you put here, you have a non-local operator, but it's always additively generated in a ball. It's additively generated in a ball. So it's there is no really operator outside the algebra generated by local operators. So it's not the idea that you have something new out or on top of the algebra of field operators acting on space, but it's just the features of the algebras and regions that give you these non-local operators, not new operators coming from somewhere else, right? These are all can be generated locally in a ball. So how much time I have? Okay, perfect. So the next example is Maxwell field, of course. Maxwell field in 4 dimensions. In D equal to 4. So here we have, again, our F mu nu, no A mu's at all. This is electric and magnetic field. And it's free, whatever. And you have that the divergences of electric and magnetic field are 0, right? So we can take a region that is like a ring. It's like a ring, and then take some boundary here and produce the fluxes of electric and magnetic fields around this. These are the fluxes of electric and magnetic fields. And immediately these fluxes are conserved. You can deform the position of the fluxes. It means that if you take a local operator, the local operator will be something produced by F mu nu, by electric and magnetic here. This flux, even if passes through it, it doesn't, it commutes, right? Because you can deform, it's the same operator, nothing happens. So these fluxes are generators of non-local operators. Let me call them the Wilson loop of charge Q. And the Toff loop of charge G is just the exponential of the electric flux. Wilson and Toff loops are non-local operators here. And then we can think, what are the non-local operators in the outside part? And the outside part, this is a ring-like region. The outside part has the same topology. So the outside part, again, will have some fluxes of electric magnetic fluxes that are non-local operators, and they do not commute to each other. The commutation relations for linked boundaries is equal to the identity, well, to I. So it means that, again, the Wilson loop and the top loop will have these commutation relations. Just exponentiating these fluxes that are Gaussian variables. This is d equal 4. This is d equal 4. Right? The usual electromagnetic field. So in this case, and all gauge theories in 4 dimensions, you will have high duality violations for regions with topology with pi 1 non-trivial, and also the complementary region has also pi 1 non-trivial. And in higher dimensions is pi 1 non-trivial and pi d minus 3 non-trivial. In three dimensions, this pi 1 and pi d minus 3 is pi 1 in 3 dimensions is equal to pi d minus 2, and pi d minus 3 is equal to pi 0. So in 3 dimensions is the same what you get from gauge theories as global symmetries. So you get the same kind of half-duality relation for the same topologies that produce the gauge fields. These are the same as the global symmetries. Okay. So here I have a commentary again that D is the space-time dimension. Space-time dimension, yes. D is 4 for the Maxwell field, so D minus 3 is again 1 in this case. Higher dimensions will be bigger, right? The commentary is the following. If you have the additive algebra in this case, that is the one generated by the electric and magnetic field locally, this is included in the algebra of the maximal algebra of R. That includes also the electric and magnetic fluxes with boundary in the ring. Of course, this thing is just a Wilson loop, right? So it's just a Wilson loop. But in the middle, you can say, well, I don't like that the theory that has these half-duality violations. So I can put some operators here, not all of them, right? In such a way that the commutant has the same structure and it satisfies half-duality violations. So it's important that these algebras, these maximal algebras, cannot be the algebra. You cannot say, well, I will take the maximal algebra for any region, because they do not commute to each other for complementary regions. So it's not good for causality, right? So, but you can take an intermediate algebra, just adding some non-local operators to this, that we call a Haack-Dirac net, in such a way that it's intermediate, and this satisfies Haack duality. Satisfies Haack duality. But of course, as you have added some non-local operators, it will not be additive, but not additivity. We call this Haack-Dirac net. Why is this? It's because in order to produce this intermediate algebra with these properties, you have to solve the the Dirac quantization condition. You want to have some operators here, non-local operators, that I label by some electric and magnetic charges. But as you have one, you have the product of the one, you have two, you have all the algebra generated you have to have, and this can be at most a lattice. A lattice in the plane of charges, that automatically contains all the products, the fusion closes, because you want an algebra, right? And then, in order that the same algebra that you put for this ring, you put for the outside part, and they commute to each other, you have to take into account that these things do not commute. You have this relation, and so immediately you get Dirac quantization condition. So you get for a maximal lattice, you get to satisfy this Dirac quantization condition. Here we don't have any monopoles, nothing. It's just an algebraic requirement. It's interesting that in the literature of generalized symmetries, these people call this the compact free Maxwell field. Somehow you take some lattice like this. But you can see here that there is nothing at all of difference between this compact thing with the usual Maxwell field. There is no way to differentiate the two. It's just, so this is a choice. You can choose this, but there's no physical thing in this choice. You can also choose any other lattice, all the lattices, whatever. There is nothing physical in this type of choices at all. You cannot differentiate physically the two choices unless you put some charges, right? You destroy the Maxwell field and you change the theory. But well, when I put some charges, I will have this. Yeah. When I put... Well, when I next I will put some electric charges, I will change the theory. It's different one. My High duality violation will be different, right? Will be different. And then if I want to, exactly, if I want to eliminate, so here you can see here that because it's important to compare what people do usually in this subject, they call to this type of thing, they call it the compact Maxwell field, without any charges, the free Maxwell field. This is not different from the ordinary field, and there is no way where you put these things. So it's just a choice. Once you want to put real charges, you are doing two things. You are first making some, or next I will talk about that. You are making some non-local operators additive when you put a charge, right? And then it will destroy some of the high duality violating operators. And then it will change. If you want to eliminate all the high duality violations, you have to put a lattice of magnetic monopoles and electric charges to the theory, and then you will have both things together. You will not have any high duality violations, and you also have additivity that here you don't have. You have high duality because you have chosen to take these things, but you don't have additivity. You don't have additivity. In order to have additivity, you have to put real electric charges, right?
So let me give you an example of this in 2 plus 1. It's again the problem we were discussing before. There is the issue of compact or non, when it's non-compact, the prefactor is infinite. When it's compact, it's finite.
The entropy is always infinity, right? You mean the topological term. You mean the topological term, the subleading term, right?
The subleading term, yeah, in particular.
Right, well, this subleading term, I will talk about that.
There is a logarithmic.
Yeah, there is a logarithmic term there. Yes.
Same is true with the scalar.
Right.
That reason,
Yeah.
compact, the coefficient of the logarithmic.
Yeah, I will talk about this in the last lecture, and this number is just an index of these Hug duality violating things. It's just an index of that.
But in that sense, that distinguishes these two cases.
Why?
Because in one case it's infinite, the other case it's finite.
Oh, of course. But then you can compute the entropies of some subalgebra that you want, right? But doesn't mean that this is physical, because you are. So it's important that when you have Hug duality, this is what I mean. When you have Hug duality violations, you can choose different algebras for the same region. That's a key point when you have Hug duality violations. You have different algebras for the same region, so you can, of course, compute different entropies for the same region. You have that. Nothing of this is physical except the fact that you can take, for example, the additive algebra, this is physical, and you can have the maximal one. And so the difference of the two is an index that can be measured, and of course you can take intermediate cases, but this index can be measured from these two different algebras. Okay, well, just to finish this. When you put QED, you have this Wilson loop, and then you have a charge operator, and this is not gauge invariant, but then you can put this integral.
Actually, the non-compact case is another operator in the line, which is gauge invariant, and it's not a line operator, it doesn't involve a line operator. I can tell you about
In the non-compact case,
in the non-compact case.
in the gauge,
Gauge theory, this goes back to work by Dirac in 1966.
you mean the Maxwell field?
Yes, for the Maxwell field.
It's another,
To create a charge, he says that's not the gauge invariant concept.
right?
You need to create the static Coulomb cloud that sits on top, goes together with it. It's a coherent state of static Coulomb.
Okay, you mean another different from this one, but
It's not the line integral. It's not the exponential of the line integral.
well, it's something is mirror of this.
No, it's a non-local operator that in the Coulomb gauge is the identity operator.
If it is the identity operator in the Coulomb gauge, it's the identity operator.
Yeah, in the one gauge, well, in the Coulomb gauge, I could take some other gauge and it's some complicated object.
All right, but once you in one gauge is an identity is identity. No, it's never, no.
Right. So there are these two. So this actually doesn't give you the honest to God electron operator in the Coulomb gauge.
The electron operator would have to have something going to infinity, right? It's different stuff.
So it has this essentially the Coulomb cloud that
Right.
has come together with it. This is different.
Yeah. I think I guess what you are talking about is how to deform this. Just it's not a line. Of course, this is a simplification. It's not a line. It can be smear or something like that. It can be spread in all space. Yeah.
The entire space.
Yeah, inside space. Yeah. This is for just for the electric charge alone, right? I'm not taking that. I don't have electric charges.
So this is, I guess, this But there is this other operator in reality. It's only in the Mach complex.
Okay, well, as we were saying, with this you can destroy the Wilson loop in the sense of it's not non-local anymore, but it's made of product of these things. So it's an additive operator, and then it means that if this has charge Q0, let's say, then your charges now for the non-local operators cannot be multiples of this. So this now belongs to 0, Q0, so it's a U1. It's a U1 group. Well, you could take when you have you have to smear, but when you have two charges, you can take the limit and then it goes to the identity. If they are you can cook up such a way. Of course, this is an interaction theory. We don't have the precise management of that to do that, but in general you can do that in a free field. For example, take two operators that are unitaries and are charged, and then you can take some limit where this converges to the identity. Or you can do it in a lattice. You can also do it in lattice. So this is a U1, and the complementary one. So now you don't have, for the complementary one, you don't have the diversion of the electric field is not equal to 0 now, but it has some charges. And that means that you cannot take, so these are still magnetic fluxes. You have still diversions of magnetic field equal to 0, so you can still take the magnetic fluxes or the Wilson loops, let's say, with these charges, but the complementary region, for the complementary operator, you cannot take fluxes of the electric field, and then you have to do something more subtle, that is the original idea of Toft, that what you do is a gauge transformation that is singular. So you take a gauge transformation in some plane here, is singular in some plane, where you take this A mu to A mu plus D mu phi, but this phi has an integral over this sigma, let's say, that jumps some quantity g. So it's a gauge transformation that is everywhere gauge, but here has a jump. But this jump can be moved in space. So the only thing that is important is the circulation of the gauge transformation. This is the Toft loop, and then you have when you put a Wilson loop here crossing this surface twice, it doesn't do anything. It commutes. It only doesn't commute with things that cross this surface with a Wilson loop. So these Toft loops are more difficult to grasp with local operators, but we know that they are made of local operators because of the von Neumann double commutant theorem tells you that, right? But of course, it's very difficult to produce them. Of course, in the lattice, it's very simple. It's just something that you can do here. It's very, very simple. In the lattice, it's extremely. It's more easy to do that than some other things. So these Toft loops have the group is the integers, while the Wilson loops have U1, and the Toft loops have a set. So what happened then when you have destroyed then some of, before it was R, and now it's U1 and Z, and if you add electric and magnetic charges, you can destroy everything, every non-local, every Hug duality violations, and then you will have a complete theory. So this is why, and in order to do that, you have to, for example, if you add magnetic charges, you have to take into account that now these magnetic charges will make additive some Toff loops, and these electric charges will make additive some Wilson loops. So better they commute to each other, because additive operators have to commute at a spatial distance. It means they have to satisfy Dirac quantization condition. So this is the idea. People say the theory is complete if you have a complete lattice of magnetic and electric charges, where here is exactly the same as saying that the additive algebra is Hug dual, has Hug duality. Well,
There's some obstructions to putting that theory on the lattice, pure Maxwell. Whereas QED, they can put on the lattice.
pure Maxwell free, you say? Yeah, well, no, we could, but making something that is not the usual way, not the usual way in which you put a gauge theory in the lattice. Well, but I showed you before, you have to put just the electric fields on along the free electric fields along the links, and the magnetic fields in the plaquettes, and just free Gaussian variables. No, the usual stuff, right? Not the usual stuff. Not the usual stuff. Here you have this. In general, you put this element of the group, and you have a gauging variable. Here, you don't do that. You just put electric fields and magnetic fields, and these do not commute if they are. So you have a version of the lattice for the free electromagnetic field. No problem. We could compute, for example, entanglement entropies in the lattice for the electromagnetic field, go to the continuum limit, no problem.
So you say the answer to my question is no. There's no relationship between this concept of completeness and some questions about
No, the answer of your question, I don't know. If you are meaning that, for example, in the continuum, the Maxwell with charges has some problem or something like that. No, I mean the Landau pole or that. Okay. No, you're not talking about that. Okay. A ver, yeah. Okay. Well, I realize that my time is over, right? Yes. So I will finish here. And